So students, today we are learning about a concept of bioenergetics. What is bioenergetics? Bioenergetics means ATP,
So your voice is breaking.
ATP which is present in the cell. You are able to see the screen, no? Students?
Yes.
Okay. Internet is little unstable. One second. Can you see the screen?
Yes, sir.
Yes, sir.
Yes. Okay. See, energy is required for every
So
living
your
organism.
voice is breaking.
Voice is breaking. Now,
Yes, sir.
even
Yes,
now it's breaking.
sir.
It's okay. Now is it okay?
Yes, sir. It's better now.
For me also it is breaking. What you are saying, I cannot hear fully. It's not continuous, not clear.
It is better now, sir.
Clear now, sir. It's clear now.
Okay, okay. Okay, students, now today's class we will learn about bioenergetics concept. Like what happens is all living organisms need energy for doing the work. So work means what? Performance inside the cell, performance as an organism in the environment. Let's say, for example, a bacteria. A bacteria has motility. How does it move? Because of energy. Without energy, there's no motility. Right? So ATP is required for flagellar movement. ATP is required for every activity inside the cell also. Like for example, replication. Then GTP is required for transferring tRNA to the ribosome site. Like that, if you think, no, every activity inside the cell has a physiology, and also externally for movement and other activities, ATP is required. See, for example, if I need to lift the duster, see the video. If I have to need to lift the duster, I need energy. If I need to talk, I need energy. So every time energy is used. When I'm saying, when you're talking about energy, what comes to your mind is always ATP, isn't it? ATP is what it comes to your mind. So let me talk about ATP first. Then I'll come back to these slides. Okay. Do you think ATP itself as a component can give energy is my question. Anyone can answer that? ATP as a component, can it give energy is my question. Try to guess.
Yes, sir.
I'm going to one slide. 1 second. I want to show that slide. Internet is a little unstable on me. Okay. See here. I think I have to come to that slide. 23rd slide. Okay. Can you see this? This is nothing but ATP. Adenine base, ribose sugar, and 3 phosphates. This is a ATP molecule. There can be a question on ATP. What is ATP? So you'll say ATP is a high energy compound. But if I have ATP like this, will it give energy? Tell me. I have a piece of cake with me. I have a piece of cake with me. I will not enjoy that until I eat it. It's only existing. I've given a clue to you. This ATP as a structure, can it give energy to you?
No, it can't.
No. Good. So you understood the concept there. ATP as a molecule cannot help you. This is another structure of the ATP. You can see here adenine base, ribose sugar, and phosphate. Okay. So please understand ATP as a molecule cannot help in giving energy. What do you see here? Hydrolysis of ATP. ATP should break down. Only when ATP will break down, it can give energy. Please keep this in mind. Without ATP hydrolysis, there is no energy. Now you can see the slide. What you can observe here. ATP has got 3 phosphates. Leave along adenosine, that is adenine and ribose sugar. The phosphates, how many phosphates will be there? Adenosine triphosphate. So between three phosphates, how many bonds can exist? See the structure there. How many bonds can exist between three phosphates? This is in violet color. Two, no? Two bonds are present.
Yes, sir.
Yeah, those two bonds are nothing but called as squiggle bonds. Squiggle. Squiggle. Squiggle bond, like squirrel. Squiggle bond. You cannot catch the squirrel, no? It's very difficult to catch a squirrel. Squiggle bond is also very sensitive. It's present between the phosphates. These squiggle bonds have to break. When the squiggle bonds break, then only energy is released. Let's say ATP is broken down to ADP. You can see down a structure, ADP plus inorganic phosphate. So one bond is broken. Is it center one? Okay, again, internet is unstable. The bond is the terminal bond and the second bond. So two squiggle bonds are there. Which bond is broken first? The inner one or the outer one?
The outer one?
The outer one is
sir.
broken first. Okay, good. The outer one is broken first. That time it gives some energy. Now please understand two laws I'll be telling you. First law of thermodynamics. Energy can neither be created nor be destroyed. Energy can neither be created nor be destroyed. You and me cannot do anything with the energy. It cannot be destroyed. It will be in some form or the other. Keep this in mind. Okay, that I'll come back to that later. So ATP is giving energy. Energy, can you see the energy? No, you cannot see the energy. It's only showing its function. Okay. So if when the terminal bond breaks, it gives 33 kilojoules per molecule. When the inner bond means ADP becomes AMP plus inorganic phosphate, around 12 kilojoules of energy is released. ATP gave 33, ADP gave 12. ATP gave 33 more. ADP gave 12. So there's a difference. Keep this in mind. So first sentence in this, what you have understood today's class, ATP itself cannot give energy. ATP should break down to give energy, you have learned. See this slide. Three phosphate groups are there. Two high energy bonds are there. The squiggle bonds are there. Okay. Last phosphate contains more energy, most energy. It gives more energy. That's what it means to say. All are cleared in this concept, first concept. Did you all understand these slides?
Yes, sir.
Okay. Now I'm shifting to another subtopic of the same. Points. These are called as points. Okay. Point number one, we have completed now. Coming to the second point. Second point, I'm connecting it with the laws of thermodynamics. The first law of thermodynamics says, see the board. Energy can neither be created nor be destroyed. Energy can, however, be converted from one form to another. Electrical energy is converted to mechanical energy is not a biological example, so no need to take that. When we turn the clock, all of you seen the old master clock? In the master clock, we have to turn the key. Then only you can make it run. The old master clock. I don't know how many of you are having. Okay. So we are converting that electrical energy into mechanical energy. Leave that example. Take the example of, this also is fine. You can take this. Chemical energy converted to thermal energy. Means the fuel is burnt to give the heat. Okay. So this best examples here, what you're seeing. Light energy is converted to chemical energy. See the down example, bottom one. Light energy is sunlight. Giving food. Food is carbohydrate. Chemical energy. Okay. So energy is in one form or the other. I want to show one more slide. Okay, I'll finish this and then go for that. Okay, let me finish up that. See here. I want this slide to show. See, energy is transformed from one form to another, from sun to plant, plant to a rat, a rat to an eagle, etc. Okay, it is just moving from one form to another. Now, one more thing you have to understand. I'll come back to delta E later. Just first law of thermodynamics you have followed. Any doubts in first law of thermodynamics? Energy can neither be created nor be destroyed. Second law of thermodynamics. The energy tend to proceed downhill from a state of higher energies to a state of lower energy. Energy is transformed from one to another, higher energy to a state of lower energy. In the sense, energy keeps diluting. How? Because whatever energy is given, all the energy is not used 100%. Some amount of energy is used by the organism. Remaining is lost as heat. Just see the example here. Sunlight, 100% is giving sunlight. In that plant can use 10%, 90% is gone as heat. Okay, the 10% was taken by the plants. In 10%, what happened? 1% food was taken by the rat, 9% lost as heat. Again, rat has got 1% of energy. Only 0.1% went to the eagle, 0.9% is lost as heat. The eagle or the bird, whichever, 0.1% is there. It's giving to the, means when it is like degraded by a fungi or a microorganism, 0.01% is taken, 0.09% went as heat. The microorganism took very less percentage and lost 0.001% was taken, 0.009% was lost as heat. We are all contributors of heat. We all play a role in contributing heat to the environment. That is called entropy. What's it called? Entropy. So all of you followed first law and second law of thermodynamics?
Yes, sir.
Okay.
Yes, sir.
Now I'm telling you an equation. What equation is it? Delta E is equal to Q into W. E is what? Energy of a system. E is the energy of a system. Delta E means change in energy of a system. Whenever you talk about energy, globally you should talk. Earth. Earth is the major one in which energy is stored. It's depending on the sunlight, of course. Delta E is equal to Q into W. The internet was unstable. Now it's stable. Okay. Audible?
Yes, yes, sir.
Okay. Delta E is equal to Q into W. Total energy of a system keeps changing. No, that's why delta E is equal to Q into W. Q is the heat energy. W is the work energy. Q is the heat energy. W is the work energy. Don't worry about Q negative, Q positive, not required now. Understand what is delta E. That's it now. Now, this equation got modified. How it got modified? 1 second, I'll show you that. This slide I'll come back if you want. Again, it's a revision. Okay, see this equation. American chemist J. Willard Gibbs in 1878 gave an expression like this. What does he say? Delta H is equal to delta G plus T delta S. What did he add, children? Can you tell me what he added here? Delta H is nothing but delta E. Total energy of a system is same, modified as H. That's all. Delta G is free energy. What do you observe other than this? Heat was modified as what equation? What is the term given now here? Q, W. No, W was work. Q is heat. How the Q is expressed here? See the equation, you can understand. Q means what? Heat, no? How are you equalizing this
Correct.
equation to
In terms of temperature,
T delta S? T delta S. Okay. T delta S is nothing but heat. What is this I'm talking about? T delta S. T is temperature, delta S is change in entropy. See, all of you feel the skin. When you feel the skin, there's some amount of warmth. That warmth came because of the heat released during the ATP breakdown. When ATP is broken down, energy is released. Some amount of energy is used to do the work. 90% energy is lost as heat. That heat is very important for a tissue or a cell to bring biochemical reactions normal, enzymes to be normal. Okay, enzymes function at a particular temperature. The temperature is obtained by the part of the heat. That is why temperature was considered one of the points. T delta S, temperature plays a role. What is delta S? Delta S is change in the heat. It won't be same. Our body temperature won't be same, but we regulate it, no? There's an organ called hypothalamus which regulates this body temperature one way. Sweating is another way. Dogs do panting, that's another way. No? So each animal has its own way of regulating temperature. That is physiology of body. That is different. Of course, bioenergetics is tough to understand unless you have to compare it and follow it up. Delta H is the total energy of this universe, of the earth. Let me take it that way. Total energy constant. A change in enthalpy of a system. T is absolute temperature. Delta S is change in entropy. Do you think we are maintaining that entropy and temperature properly? No. See this picture. 1 second. See this picture. Sunlight is giving, solar energy is used by the plants. Plants synthesize food, eaten by animals. No? Every organism, then microorganisms degrade plants as well as animals. So every organism contributes some amount of delta S. That's what you take home message in this slide. Delta S is written from tree, delta S is written from animal, delta S is also produced by microbes. All of us contribute. But see the right hand side picture, similar picture is there, but something else is added. Can you tell me what is added in the picture? Yes. What is different? Leave plant, sunlight, microbes, man and all, leave it. What is there additionally? In the colored picture, children, what is there? Can you see something burning? No. Burning?
Coal.
Coal or wood. When you burn it, it gives heat. Okay, that is change in it. That's adding entropy. It's adding heat, which is not required. Vehicles, pollution gives heat, which is not required. If those were not there, then man and animals and plants would have given a normal entropy from our body to the environment. But we are increasing heat and leading to global warming, which is not anyway required now. Let us not talk about it. This picture tells about only energy movement from one to another. Consumers, from producers to herbivores, herbivores to omnivores, omnivores to carnivores, carnivores is degraded by, eaten up by detrivores, and finally microorganisms will degrade everything. Anyway, that's fine. I want to show one more slide relating to this. See here, 1000 joules of energy, of light energy came, 10 joules were used by the plant, the producer, 10 joules were taken from the plant, only 1 joule is retained in the herbivore, 9 joules is lost. See, 1 joule is taken by the carnivore, among which 0.1 is used, 0.9 is lost. This all tells about second law of thermodynamics. One more thing. This equation delta G, why have I written this here? Delta H is equal to delta G plus T delta S, right? We can calculate delta G. How? Delta G is equal to delta H minus T delta S. Okay, that's one thing we should remember. We can rearrange and write the equation. All reactions which are present thermodynamically in the cell, sometimes energy is lost given when a reaction happens. That is called negative delta G, means exergonic. Whenever energy is used for a reaction, it is called endergonic. Exergonic reaction, endergonic reaction. Exergonic reaction, negative, minus delta G. Endergonic reaction, plus delta G. It's used. Okay. Till here, all of you followed it? Concept of bioenergetics?
Yes, sir.
Okay. Arshit, take the attendance, Arshit, meanwhile. I'm just seeing if any point.
Yes, sir.
You've taken. Thank you. I'll send you notes for this. Some points is enough, actually. They can ask 5 marks question on concept of bioenergetics. And they can ask another 5 marks question on high energy compounds. So I'll be teaching you 2 topics here. I'll send you the notes for this, whatever I taught you today. Means points I'll send you. You can take screenshots also. Have you taken screenshots of this? Anyone? Or shall I forward it in the group?
Sir, please send it in the group.
Yeah, I'll send it in the group. These are just for knowledge. From here, I will start. Next class, I will be teaching you from here. I think tomorrow I have a class for you, no? See this slide. ATP gives ADP plus inorganic phosphate, 33 kilojoules per molecule. When ADP breaks down, that time it gives only 12 kilojoules of energy. That's the second squiggle bond I've written here. So squiggle bond. From here, I will start. This is the second part, that is the high energy compounds. Okay, so 2 parts we'll be studying. After that, I will teach you biomolecules, 1 or 2 important classes. We'll just discuss the main things. Okay, so it will wind up with that. Okay, okay, students, any doubts still here? We might de-link anytime, less than a minute. Take care. We'll see. Please tell them to attend classes. Don't miss the classes. Okay. I'll stop at this point. I'll meet you. Maybe tomorrow we'll conclude this part, topic. And 1 more 2 classes we'll see. Monday, Tuesday, revision also we'll do. Okay. See you, students. Bye.
Thank you, sir.
Thank you, sir.
Okay.